Hello and welcome back to this video series about the Intermediate Math League of Eastern Massachusetts. Today we're going to be finishing up the number theory section, looking at least common multiple, and then looking at how we can apply least common multiple and greatest common factor together. Now, if you're unsure about what greatest common factor is, I would recommend watching my first video on number theory me too, where I explained that because we'll be using it in today's video. So the first thing that we're going to talk about is the least common multiple, which is also abbreviated as LCM. So the LCM is just a relationship that can be drawn between two numbers. So the relationship is that when you have two numbers, A and B, the LCM will be the smallest number that's a multiple of both A and B. Now the name of LCM is least common multiple, so that makes sense, because least as in the lowest, common as in they both have this number as, and then multiple as a multiple. So it's the lowest number that's a multiple of two numbers that you're working with, which we're calling A and B. So let me give you an example. If we're trying to find the LCM of 6 and 9, we would find it to be 18. And the reason why is because if we list out all of the multiples of 6 and 9, we find 18 to be the lowest number that's a multiple of both. The multiples of 6 are 6, 12, 18, 24, and so on. And the multiples of 9 are 9, 18, 27, and so on. Well, we can stop there already because 18, we already noticed, is a multiple of both numbers. So now we just need to make sure that it's the lowest number that is a multiple of both. And it actually is, because none of the other numbers that are multiples of either 6 or 9 are shared. 18 is the first one, which would make 18 the lowest common or the least common multiple of 6 and 9. However, the best way to find the least common multiple, especially if you're dealing with bigger numbers, is rarely to list out all of the multiples of those numbers. So I'll be showing you one way to find the least common multiple in the next slide. So as I said, there's one main method for finding LCM. And that's that you have to find the maximum degrees of prime factors of both numbers multiplied. So that might be a little bit confusing, so I have an example here. And I find the best way to explain how this method works is through example. So we're going to be using this method to find the LCM of 90 and 594. Now the first step is to find the prime factorization of both numbers. And the reason why is because we need to find the maximum degrees of the prime factors of both numbers. And the only way that we can get all of the prime factors of both of these numbers is by first finding the prime factorization. So I'm not going to spend time using the tree diagram to find the prime factorization of both numbers. I actually have it written down right here, just so I can show you how this method works, but you would have to use the tree diagram and actually find the prime factorization of both numbers in order to do this method. So the prime factorization of 90 is 2 times 3 to the power of 2 times 5. And the prime factorization of 594 is 2 times 3 to the 3 times 11. So our method says, find the maximum degrees of prime factors of both numbers. Well, so I'm going to circle part of this definition and explain to you what this means, because it might be a little bit confusing. And it's the words maximum degrees. So a degree of a number is essentially just what exponent it has. And what I mean by that is if a number has an exponent, then it's a degree of whatever number has that exponent. So let's take the number 2, for example. Let's say we had 2 to the 0 and 2 to the 5. These would be different degrees of 2, and 2 is our number that we're multiplying by ourselves because it's the one that has the exponent. And they'd be different degrees of 2 because they have different exponents in them. So some different degrees of 2 might be 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on. And this applies to any number. If a number has an exponent, then it's a degree of that number that has the exponent. So what we need to do is find the maximum degrees of each of the prime factors of both numbers. So we'll start with our prime factor of 2. Both numbers have 2 in the prime factorization. And in both of these prime factorizations, it's actually just 2 to the power of 1. Because when you just have the number 2 or you have any prime factor on its own, it means it's the power of 1. So now we need to find the maximum degree of the prime factor in either of the prime factorizations. Well, the maximum degree of 2 that we see in either of the prime factorizations is just 2 to the 1. Next, if we move on to 3, 3 is our next prime factor in both of these prime factorizations. So we need to find the maximum degree of 3 in either of the prime factorizations. Well, the maximum degree of 3 that shows up in either of these prime factorizations is 3 to the power of 3. Now we have 3 to the power of 2 in the prime factorization of 90, but 3 to the power of 3 is a higher degree, and it's in the prime factorization of 594. So that's what we're going to use in our calculations. Next, in 90, we have 5 to the power of 1. And since this is the only 5 in either of the prime factorizations, and since it's to the power of 1, the highest degree of 5 that we have is just 5 to the power of 1. And then in 594's prime factorization, we have 11, which is also 11 to the power of 1, because it's the same thing. And since 11 doesn't show up in any other place, and we only have 11 to the power of 1 here, 11 to the power of 1 is the highest or maximum degree of 11 that shows up in either of these prime factorizations. And you might wonder why I'm circling these numbers. It's because the numbers that I circled are the numbers that we're going to use to find our LCM. Specifically, all of these numbers here. So now that I have them circled, we just need to figure out what to do with them. Well, if we look back in our method definition, it says, find the maximum degrees of prime factors of both numbers. Great, we did that. Multiply. So now we just need to take these numbers and multiply them all by each other, which means that the LCM of 90 and 594 is going to equal 2 times 3 to the power of 3 times 5 times 11. Because now we found the maximum degrees of each of the prime factors in either prime factorization, and now we just need to multiply them out in order to find least common multiple. And then if we multiply that out, we get that the least common multiple of 90 and 594 is 2,970. All right, so now I have a practice question about least common multiple. If you'd like to try it, I'll give you a few seconds to pause the video, and then I'll explain how to find the answer. So the correct answer to this question was 2:14 p.m. So the question says, Jason and Jake both start running laps around a track at 1:50 p.m. If Jason runs one lap every 6 minutes and Jake runs one lap every 8 minutes, what time will it be when they simultaneously arrive at the starting point again? And it's asking us for a time as our answer, which is why our answer is 2:14 p.m. So it's a little bit tricky if you're trying to work with times in your questions, because it's easier just to work with straight up numbers, whereas times have the hours and minutes system. So what we could do is we could actually find how many minutes after they start, they'll arrive back at the starting point again, and then add that to 1:50 p.m. And if you're confused on what that means, it means, like, say they take 10 minutes total. They arrive back at the starting point again simultaneously after 10 minutes, then we would just know that they arrived 10 minutes after 1:50 p.m. back at the starting point, which would give us 2 o'clock as our answer. And so all of a sudden we have a much more simple question where we just need to find how many minutes after they start will they arrive back at the starting point again simultaneously. So now our next job, since this is a word question and we need to figure out what math we need to do to find the answer. So our next job is to find when they'll arrive back at the starting point again. Well, if Jason runs a lap every 6 minutes, and he starts at time 0, then after 6 minutes, he'll be back at the starting point. And then after the next 6 minutes, which is at 12, he'll be back at the starting point, and then at 18 and 24 and so on. And we'll notice that all of those numbers are multiples of 6. So at every multiple of 6 minutes, Jason will be back at the starting point. And then the same applies to Jake, but every multiple of 8 minutes. So at 8, he'll be back at the starting point, and then at 16, 24, 32, and so on, all the different multiples of 8. So really, if we know that they'll be back at the starting point at multiples of however long it takes them to run one lap, then all we need to do is find the least common multiple of how long it takes each of them to run a lap. And since it takes 6 and 8 minutes, we only need to find the least common multiple of 6 and 8, which means that we need to first find the prime factorization of both of those numbers. So we'll start with 6. We write 6 at the top of our tree diagram, and we break it down into 2 different factors that multiply to get 6. Well, it only has two factors that aren't itself and 1 that multiply to get 6. Those are 2 and 3. And since 2 and 3 are both prime numbers, we actually finish this prime factorization really quickly. Next, we have to find the prime factorization of 8. So the prime factorization of 8, we use 8 here at the top of our tree diagram. So we just need to break 8 down into two different numbers that multiply to get to 8. So I'm going to break it down into 4 and 2. And then we look and see if we can break down any of these numbers further. And we can, because 4 isn't a prime number. So if we break down 4, we'll break it down into 2 and 2, 2 and 2. And now at the bottom of our tree for 8, we have only prime numbers left. So now we have the prime factorization of both numbers. For 6, it will be 2 times 3. So you have a 2 and a 3 at the bottom. And for 8, it will be 2 times 2 times 2. And then when we write those in exponential notation, here we still have just 2 times 3, but I'll write 2 to the 1 and 3 to the 1, just for the purposes of what we're doing. And then here, since it's 2 multiplied by itself 3 times, we have 2 to the power of 3. So now if we write our prime factorizations over here, our job is to find the maximum degree of each of the prime factors that show up in either number, right? So we'll start with 2, because 2 is a prime factor that actually shows up in both of these numbers' prime factorizations. Well, in the prime factorization of 6, we have 2 to the power of 1. And in the prime factorization of 8, we have 2 to the power of 3. And 2 to the power of 3 is the higher degree because it has a bigger exponent, which means we'll use this in our calculations. And then next, the only other prime factor we have is 3, and it's only in 6, which means that we just use this value of 3 to the power of 1. Just 3 to the power of 1 is the highest degree of 3 that shows up in any of the prime factorizations. And now we don't have any other prime factors that we didn't account for left, so we can just multiply these out to get our least common multiple. So we multiply 2 to the power of 3, which simplifies to 8, because remember, that's just the prime factorization of 8. So 2 to the power of 3, which I'll write 8 in the place of, and multiply that by 3 to the power of 1 times 3 to the power of 1, which is just 3. And when we multiply those two together, we get 24, which means after 24 minutes after starting, both of them will simultaneously arrive at the starting point again. And we know that's true, and I'll just check this and show you how to check it. Because if we just listed out all the factors of 6 and 8, which I can just do off the top of my head because they're smaller numbers, we get 0, oh sorry, 0 is not a multiple. Okay, 6, 12, 18, 24. And for 8, we have 8, 16, and 24. And 24 is the first time that they actually have a multiple in common. So again, it'll be the first time that they arrive at the starting point after they start, or how many minutes after they start they'll arrive at the starting point simultaneously. So now that we know they arrive at the starting point 24 minutes after they start simultaneously, all we need to do is add 24 minutes to 1:50 p.m. Well, we can break this down into 10 minutes and 14 minutes just to make it a little more simple. So if we add 10 minutes to 1:50 p.m., so 10 minutes after 1:50 p.m. would give us 2 o'clock. And then if we add the remaining 14 minutes that we divided up into just for simplicity, we would get 2:14 because it's 14 minutes after 2 o'clock. So they would simultaneously arrive at the starting point again at 2:14 p.m. Okay, and the last thing we need to talk about is LCM and GCF relationships. So when dealing with least common multiple and greatest common factor, there's actually a formula that can be used to create a relationship between the two of them. So the formula goes like this. The GCF of n and m times the LCM of n and m equals n times m. So basically what this formula means is that when you have the GCF of two numbers, which in this case we're calling n and m, and then you have the least common multiple of two numbers, when you multiply that GCF and LCM by each other, that will just equal the product of the two numbers themselves. So let me give you an example. The GCF of 6 and 9 times the LCM of 6 and 9 will equal 6 times 9. So the GCF of 6 and 9 is 3, and the LCM of 6 and 9 is 18. So 3 times 18 should equal 6 times 9. And then if you multiply those out, you get 54 equals 54, which means that this formula works. Now this formula would be used practically in an actual question. Say if you knew what the LCM of a number is, so you know what the LCM is, and you know what the GCF is, and then you also know what one of those numbers is themselves, you could multiply the LCM times the GCF. And since you know that this multiplies to the two numbers that you're finding the LCM and GCF of themselves, you could divide by the number that you already know, which we'll call n, and that will give you the value of m. You could just use it to find whatever value is missing, like you would in any algebraic equation. Alternatively, you could also use this if you knew the product of n and m, or n and m themselves, and then you also knew either the LCM or GCF. You could divide the product of m and n by whichever one you have, the GCF or LCM, to find the other one, instead of going through all the extra calculations with the first methods that I taught you to find either of them. So now I have a review question about this concept. So if you'd like to try it, I'll give you a few seconds to pause the video and then I'll explain the answer. So the correct answer to this question was that y equals 45. So the way that we would find the answer to this question is just by using the formula we just learned. So the formula says that the GCF of two numbers times the LCM of two numbers will be equal to the two numbers multiplied by each other. So GCF times LCM, and I'm actually going to use this symbol for times, and I'll show you why in a second. This just means multiplied by equals the two numbers multiplied by each other. So our numbers are x and y, x times y. And the reason I use this symbol for multiplication is because if I use the x for multiplication, well, that looks exactly like the variable x, which is why a lot of the times when we're talking about variables, we use this symbol for multiplication instead. So the GCF times the LCM of these two numbers will be equal to the two numbers multiplied by each other. Well, we already know the GCF and LCM of the two numbers, and we know what the value of x is. And all we have to do is find y. So first, let's substitute our values into the equation. GCF is 5, and the LCM of the two numbers is 225. And then those multiplied by each other will equal x times y. And then x equals 25, and then we don't have a value of y. That's what we're trying to find. So I just keep y as itself in the equation. So the next step is to multiply 5 times 225, just to simplify our equation. So 5 times 225 will be equal to 1,125. Then that's going to equal 25y. And now this is a little bit of basic algebra. Basically, we want to get y all on its own, right? We don't want to find the value of 25y. We want to find the value of just one y. So in order to get rid of this multiply by 25, we have to divide both sides of this equation by 25. 1,125 divided by the value of x, which is 25, will give us 45. And then if we divide the other side, 25y by 25, that gives us just y. So 45 equals y. So we take the product of both our GCF and LCM and divide it by one of the numbers that we know, which is 25, to figure out whatever's remaining, which is 45, will be equal to our value of y. All right, just to quickly review what we've learned this lesson. So first we talked about least common multiple, which is a relationship that can be drawn between two numbers. And that relationship is that the LCM of two numbers, a and b, will be the smallest number that's a multiple of both of them. And so we looked at an example where the LCM of 6 and 9 is 18, because if we list out all of the factors of 6 and 9, we see that 18 is all the multiples of 6 and 9. We notice that 18 is the first multiple that they have in common, which makes it the least common multiple. And then we talked about how to find the LCM of any two numbers, and there's only one method for this, and it goes like this. You need to find the maximum degrees of the prime factors of both of the numbers multiplied. So we used 90 and 594 as an example to explain it. The first step is to find the prime factorization of both numbers. The second step is to find the maximum degrees of the prime factors that show up in either of the numbers' prime factorizations. So we circled them like this, where it is 2, 3 to the 3, 5, and 11. And then you just have to multiply those out to get your LCM, which in this case is 2,970. And then we did one word practice question relating to LCM, where we found that Jason and Jake would both meet up again or simultaneously arrive at the starting point after starting their running laps 24 minutes after they started. So if we add that to 1:50 p.m., which is the time that they started, the answer to this question will be 2:14 p.m. And then we talked about LCM and GCF relationships, which was pretty simple. We just learned one formula that says the product of the GCF and LCM of two numbers will equal the product of those two numbers themselves. And then we looked at an example of when this works, which we found the GCF of 6 and 9 and the LCM of 6 and 9, which is 3 and 18. And so we multiplied those by each other, and that equals 6 times 9, because 54 equals 54. And then finally, we did one review question where we applied the formula that we had just learned into figuring out that y was 45 when we know the GCF, LCM, and one of the numbers that we're finding the GCF and LCM of. So that's all I have for this video. I hope this was helpful, and it's actually the last video for number theory me too. So next time we'll be starting arithmetic, and I hope you enjoyed it.